It is 3 o'clock, and so I am going to get us kicked off. Welcome, everybody, to the Inspiring Innovation in Student Research workshop series this summer. I am just kicking off. I see you, Keaton, in the chat asking, we're just getting started, and I want to let everybody know that the sessions are being recorded. We are really excited to be kicking off our first ever virtual session series with you all this summer, and we're glad that you were able to join us. You are welcome at any point in time. I right now have all participants on mute, but you are welcome at any time that you have a question to jump in the chat, or you can also, if prompted by the facilitators, jump on that microphone and ask your questions aloud. We do ask that to keep background noise down. If you are not engaged in talking with the whole group, that you keep your microphone on mute. If you've not been in Zoom before, I just want to give you a quick orientation. You should, at the bottom of your screen, if you mouse over the bottom of your Zoom session, see your controls. And so you can use those controls to jump into the chat room. It just says chat. If you click on that, you will find the chat function. If you are just joining us, I did put into the chat for everybody. Oops, I apologize. I'll do it again. The sign-in form that is both on the Google site, and I also just dropped that link in the chat for everybody. So if you are seeking CEUs, it's really important that you sign into today's session. Those sign-ins are time-stamped, so we will ask you to sign in each Tuesday as you join us. Sign into that Google form, and we will be able to award certificates for those who participate in all of the sessions, and also submit the assignments, which will be very relevant to what we're working on and relevant to what you're doing with your students. And with that, I am going to just quickly introduce myself. I'm Teresa Gibson, the Executive Director of the North Carolina Science Fair Foundation. It's nice to meet you all. And I will introduce our facilitators today. Judy Day, who is the Foundation's Director of the State Science and Engineering Fair, and Manley Midget, who is our Outreach Director. These two have done our workshops for many years and have a wealth of experience. And with that, I will throw it over to Judy. During the session, if you have any specific questions or technical needs, you can feel free to chat me or reach out via email, and I can help you throughout. With that, I will throw it to Judy.
Thank you. I would like to again welcome everyone. This is going to be a new experience for me. I've done this workshop a lot of times, but never virtually. So we'll see how it goes. Transition overward. First of all, I would like to point out our website that's in the bottom of every page. And that's where most of you, I think, registered for the sessions. And that's the www.ncsef.org. There's a lot of good information in there, and we'll be adding to it a lot of presentations, videos, and pitch photographs that students have sent to us who qualified for the State Science and Engineering Fair that we had to cancel. So I really encourage you to look at that and to be able to enjoy the students. We talked a little bit about, I think Teresa mentioned about the CEUs. I know that there are not a lot of things going on this summer to give you some CEUs. So we do offer one CEU credit if you are able to attend all 6 of the sessions. And if you can't attend one, we will be recording it, but I think it's always nice to be there live if at all possible. We will be giving you a few homework assignments to be able to do, nothing drastic, but things that we'll be talking about during the following sessions that you need to have done. Once you do the homework, you'll need to email it to either Manley or myself. And Manley is going to be getting all of those who teach elementary, and all of you who teach middle school and high school will need to send the homework assignments to me. And that way we can compile them and be able to use them in the presentations that we have following the assignment. We will be sending out a complete final evaluation, and that will be coming from Teresa. And that will need to be emailed to her at the exec director at ncsciencefair.org. And once we receive all of that, then we will be able to send you that certificate with the 1 CEU's credit, which I know will come in handy for you.
if you're not in the classroom, you might want to, so you might not be elementary, middle, or high. You know, if you're a parent, or if you're a supervisor or a STEM coordinator, somebody like that, you might want to just choose one. You can send elementary. If you have more of an affinity to elementary, you can send that to me. If you're more toward middle, high, you can send that to Judy. So you don't have to be a classroom teacher.
Okay. And it's not. There we go. We will be talking about doing scientific research that you can do with your students, whether or not you have them in a competition. But since we are affiliated with the North Carolina Science and Engineering Fair, we'll be referring to the rules and regulations and timelines and things like that that go along with the fair itself. In order to participate in the fair, you first, at the state level, you first have to qualify for one of the regional fairs, and then qualify for one of the regional fairs to come to the state level. And North Carolina has divided up into 9 regional fairs, and we've got a map in there. You can see how that's divided up. That's also on our website. Region 3 actually is divided up into 2 regional fairs, but Region 3B is only for the North Carolina School of Science and Math. And that's the only students that participate in that. Although there are some students that take their online and that sometimes will partner with a student that's there in person and participate in that. So looking at the schedule for these for the entire series of sessions, I said for the end of this session, it's really for all of the series. We really want everyone to leave with a good understanding of what the research process is all about. To be able to have more effective strategies and processes to be able to engage your students in STEM related research. And the research that we'll be talking about is not just science research, but also engineering, mathematics, technology, and we really want to have our students branching out, looking at everything that's in that STEM related areas, and becoming more active and finding something that can really turn the student on and maybe get them to consider careers in the future, or at least make them much better consumers along the way. When you're doing research, whether you're doing it at the school level, elementary, middle, or high school, at a university or in a corporation, they all have to abide by rules and regulations. And sometimes our students don't understand why we have rules and why we have regulations that they must follow in order to be able to qualify for the competitions. But that's the way it works. That's the way scientists work. That's the way engineers work in order to be able to do the work, what they do. There are rules and things that they have to follow. And it's the same with your students and what they will need to be looking at as well. So we'll talk a little bit about those rules and how we can make it a little bit easier for you to share those with your students and get them to comply. Mostly we are looking at a lot of those rules to keep your students safe. And that is foremost in everyone's mind when they're working with maybe materials that they're not as familiar with, is that safety is primary in our importance. And we also want them to understand something about research ethics and how that works, because that also comes into play. We'll talk a little bit about our website, about several other websites that we want you to be able to share with your students and teachers, other teachers, parents, and members of the community to be able to help make the whole process easier for them.
This is Manley. Judy, before you go on to the next slide, one thing, I didn't introduce myself. I was in the original group way back that restarted the science fair in North Carolina and led that for a good number of years. And then Judy and I have been working together, and she's been the director for a good number of years now. So my background is long in the science fair. And some of you might be wondering, well, gee, I signed up for this workshop and I didn't know it was just all science fair, and it's not. One objective that's not up there, one outcome that's probably the most important one for me, and the activities I'll be doing with you is I like to show you some ways that you might be able to change what you're doing in your classroom so that it can be more inquiry based for your students. Less cookbook, but more heavier on the side of them learning science skills and how to do things and how to solve problems on their own. So hopefully we'll shake up your thinking a little bit, and you'll take some of the activities that you already do in the classroom that are really good, and you might make them even stronger by getting a little more inquiry in them. And so we'll talk about that as I do activities with you throughout the workshop. And on the bright side, if your students really get into the inquiry idea and want to do some open inquiry and want to get into some science research, you'll be set up and ready to go, ready to guide their research inside and outside the classroom. So anyway, that's a goal I have, Judy.
Great. All right. Thank you. So one of the questions that I get often from, why should we do this? And after having worked with a lot of students through the years, I've been doing this since 2003. I've seen a lot of changes in students and a lot of excitement that they have had when they have really been into the project. And so one of the things that I really like for you to think about is getting these students excited about doing the inquiry-based science. That science is fun, science is engaging, science is, we're constantly adding to our pool of knowledge, and it needs to be something that's alive and that they can be excited about. They also need to learn about how to approach a problem to be able to solve it. And scientists and engineers have definite steps that they use in order to be able to get the answers to what they're looking for, that problem they may have. And a lot of these steps transfer into everyday life, of being able to take that stepwise process of getting the background information. And it gives you those lifelong learning skills of organization, getting that time management in. You can't put things off to the last minute. We'll talk about that, about how that works and how you can help prevent that with your students to kind of force the time management upon them. It also gets those students to become experts. And that's when it's really fun, is you can see them light up as they start talking about what they've been working on, the research they've done, and what they've learned. And that's when they really start thinking about, maybe I could do this as a career. That natural curiosity that our toddlers have and our kindergartners have sometimes gets drowned out by the time they get to be in middle school and high school. And that natural curiosity is what in the past has set the United States above some of the other countries in coming up with new methods, new ways of doing things. And we need to make sure we get that natural curiosity going back again with our students. And for the NGSS, the Next Generation Science Standards, what you do with students, when you teach them how to approach things through a scientific approach or through an engineering design approach, you are working step by step with that Next Generation Science Standards along the way. For teachers, I know that in high school, you're a lot more separated, and so you don't see the working together across the curriculum as much, but in elementary and middle school, it really comes into play that you're doing things when they're working on a project that goes across the reading and the writing and the content areas, including the math and being able to collect the data and analyze the data. What's the best way to present the data along the way? How can I create a graph to be able to show what I want it to show? Which kind of graph do I need to use? Being able to understand whether this data is significant or not, or whether I need to collect more data to be able to say, yes, this happens or not. That interpretation. So a lot of it is getting that science literacy and getting the students interested in science and engineering, motivating them to pursue those types of careers. But above all, it's increasing those critical thinking skills that we need in whatever discipline we go into, in all walks of life, of being able to think through a problem and learn how to solve it. So these are all real world skills that you don't have to be a scientist or an engineer to need these types of skills of the critical thinking and solving problems. And again, so there's a process, and there is a link that's right up at the top to Science Buddies. And let me see if I can switch out to this to pull it up for you and show it to you. Okay, so I have, and I've expressed this frequently, and I'm not sure you're seeing this. Is that, are you
Judy, we're
anyways
not. I think you must have.
not?
No, I think you must
Okay,
have just
so I
shared the
need
deck.
to stop my sharing because I am sharing only the one thing, and share this one. Okay, so this is the Science Buddies website. And I have a love-hate relationship with Science Buddies. They have some really nice material in there for teachers to be able to use. They have some good information for students to be able to use. They also have a lot of projects that they tell you from the beginning how to do that project. And unfortunately, I get a lot of projects that come in that that's straight from Science Buddies. And if the students choose to use a project that's listed in Science Buddies, it's not original research. So it would have to be listed in their bibliography, and that would be background information. And they would need to come up with a different question that they're asking about that topic. For you working in your classroom, however, sometimes that can be a good way of students getting started. But what I came to the site to is to show you where it has the science fair schedule worksheet. And I think Teresa may have sent that link to you of this website. But this worksheet gives you a list of all the different activities that we will be talking about during the next couple of sessions, a suggestion on how long to give your students that assignment, how many days. And then it also has grading rubrics to be able to use with that. So let me see if I can go back now and stop my screen sharing and go back to the presentation. There we go. All right, maybe by the end of this, I'll figure it out. Okay, so looking at a timeline, summer is the perfect time to get started on this because you need to look at what the school year is going to be. And this year, who knows what this year will be? I mean, who knew that we would be getting out of class in the middle of March? But this is something that even if you are doing virtual classes, you can talk to students about picking out something that they would like to do research on and coming up with a topic and doing the background information and developing a research plan, and then approving those along the way. So it will be even more important if you're doing something like this virtually to be able to keep tabs on what they're doing. And that goes along with the rubric that Science Buddies suggested. For you to be able to think about the time, you'll need to look and check what they have done so far before they go to the next step. This is definitely not a science fair week. I really think that the best projects take place over an entire semester. ISEF has rules that say that you can work on a project for an entire year and present it within 18 months of the time that you start your experiment. So if worse comes to worse and we don't get into the classrooms until later this semester or even the beginning of next year, they don't start counting that time period till they actually begin experimenting, not the time that they spend developing their topic and background research and research plan. So we'll talk more about that. But when you're setting your timeline, you're going to need to look at when you're going to have available, when they're going to be holidays. And again, we're flying blind on this one. So just think about when you want them to get through and then kind of backtrack. They're going to need time for doing
backwards. That's the key, Judy, I think, is working backwards. You know when you got to submit a project if you want to go to the regional level or when you want to have your school fair, and you got to work backwards from that.
I know. And this year, most all the regional fairs take place, except for the one in Region 7, and that Region 7 is earlier, but all the rest of them take place in February. So I would shoot for, if you're going to have a school fair, to take place by mid-January, and go from there. So you're going to have time for the designing things and actually creating that research plan, getting it approved, making sure there are no safety issues along the way, that they've gotten all the different approvals that are needed if they're working with humans. There's special issues working with humans. Just like when you take students somewhere, you have to have special permissions to take them on a field trip. It's the same way if students are asking questions with other humans, and then there are issues that you have to work out. The same with animals or any hazardous materials. They need to have time to actually do the experiment after they've done that research plan, had it approved, and to be able to analyze the data that they've collected, and then to put it all back together, whether it's going to be a research paper or a project board. And I really suggest putting it together in some sort of a paper, because for the student, it pulls it all together from the beginning to the end, and they're able to see what they've actually accomplished. If they have a school competition, then that's going to be the date that you're going to work back from. If they don't, then you can work back maybe from the regional fair to be able to get that. It's nice if you can give the parents some information early on, saying, these are the things that I need you to help me with. I do not need you to do the project, but it's nice that if they need assistance going somewhere to collect data or asking questions to people or whatever. And that's another place that Science Buddies has a sample letter in their package for the teachers that you can use in helping you craft what you can send out to the parents. Guiding the students through the process for you is very important, and you're asking questions to get them thinking about what their next step will be. How are they going to approach a problem? How are they going to solve that problem? And then, of course, if you want to have the students present, it can be only in your classroom, and that can be as far as you go, and let each student present what they have been working on. You can divide up curriculum that you're teaching and have them each present something. Or it can go to a local level or to the regional or even to the state level. And I take high school students to the international competition usually. So at the students, it looks a little bit different because you're going to be directing them on what they need to do. The first thing is probably getting started. And this is one of the hardest things. So they need to think about what they are interested in, some of their problems they have in their own life, things that they could maybe do to make life easier, things that they enjoy doing, whether they enjoy playing ball, they like probability and playing different types of games. Think about what they are engaged in, what they like to do to help them come up with their own problem or their own question. Here again, if you are doing this as a classroom activity, one year in the past, I taught biology, and there were more chapters than there were weeks of the year if we taught the full year. So in some of that, I let the students pick a project, and we weren't going beyond the classroom, but they were able to select a topic, in the book, and then they would present that in addition to what I was doing to add to what the students had, and we did it at the end of the year as enrichment. To be able to reinforce information that they had gotten throughout the entire year. So it depends on your situation as to how you want to do it. With all of this, you want your students to start journaling. And journaling is something that research scientists and engineers do all the time. Everything they do is journaled. They write it down. And if you're in a research lab that is possibly going to be going towards patents later, it has to be verified by other people that every day before you leave, someone else has to sign that journal, and this is what you've accomplished and this is what you did. So that if it ever comes to a patent disagreement, they can go back to that journal. So getting students to write about what they are doing is going back to that curriculum of the reading and the writing and the content area, and getting them to make a habit of that. Start with when they're looking at what a topic would be that they would want to do. Then once they select that topic, they do background research on that topic in order to be able to find out what we know, so they can come up with a question of what we don't know that they would want to answer. And then they have to develop that testable question. So their background research, they'll be keeping a bibliography in their journal and notes of what they have learned. And then once they get into developing that question, all of that, again, is in the journal. Developing their research plan, materials that they're going to be needing, safety issues they're going to need to address, special permissions that they might need to have. All of that comes before they ever begin doing an experiment with an approval. Then they actually conduct the experiment. Some of them take a long time, over weeks. Some of them may take just a few minutes to run through one time. Then they have to repeat it over and over and see if they can get the same results. Learning how to analyze those results and putting it together in a way that other people can understand their data, to writing up their findings, graphs, charts, writing it in text, and then creating a display or writing a research paper that they might want to share, and then presenting that wherever it may be, whether it's to a class or whether it's to a greater audience along the way. And I've been kind of going quickly, but I haven't asked, my chat window disappeared. So I'm going to put that back in there. And Teresa, I'm going to ask, have you been seeing?
Yes. So, and thank you for pausing. I'm getting a couple of questions about the virtual aspect. And I did write, I'm happy to talk to anybody about what we're thinking right now for if we have to go virtual. And we are looking at that as an opportunity also, maybe to be able to reach more students. But one other thing I would add is that Manly and Judy have been working very hard to figure out how do you realistically do inquiry-based science virtually, and you will see the process taking place throughout the workshop series. And Manly has tried very hard to stick to household items that people would have available to them in their home, even students. You'll see with our first inquiry experience that they are very readily accessible items. And so I just wanted to let folks know that too, that you will see a model of all of these pieces being done virtually.
Okay, great, thank you. And Teresa, feel free to hop in there because I need to have my watch here in front of me. But
Are there any other questions? Any other big questions, Teresa?
Those are the ones I've been getting, but we can pause right now. And if folks want to jump in the chat or on the microphone, if you have another thing rolling around in your head.
Okay, all right, so let's get going. If you're a teacher, you know you have to grade things or else students don't think it's worthwhile doing. My days in the classroom, it was kind of like, you know, I'm having to grade this because you won't do it unless I grade it. So that's part of living. Each portion that I just was talking about, of the student portion, is a separate grade. And the reason for that is that I really strongly feel that students learning the process of being able to tackle a problem and learning how to answer questions is much more important than they're coming up with that Einstein project, because they're not all going to be Einsteins, but they all are going to need to learn how to address problems and solve them, and regardless of what they do. So by checking them along the way, you also know that it's being done. You can see what the student is doing instead of the parents coming up with the project the night before that it's due. You can put that feedback for the students to be able to maybe get them going towards a little different direction if they need to be steered in a different direction, or to reinforce what they're thinking is a great idea, or help them problem solve. Where can I get materials that I need, or who can I ask the question about this with? So,
Judy, I think if we could pause right there, there's another question that just popped up about Science Olympiad. So I don't know if you or Manley wants to take this, but it is just that if students are doing a build with Science Olympiad, is that eligible for science fair?
yes and no. And I'm going to let Manley jump in and be more specific, but if the students are going to take it to a science fair competition, the maximum number of students on a team is 3. So if they only have 3 people working on a build or less, 1, 2, or 3, then it can be used as long as they also are filling out, doing the process that we're talking about, to have that. So they're working together. So they're doing the Science Olympiad, but they're also creating that research plan of how I'm going to be doing it. So Manley, you are the Science Olympiad expert.
Yeah, I did that. I was the director for like 23 years and helped start that, and we're still doing that. Still working with it. And Kim Jervis is the director. Whoever asked the question probably knows that. I work with the construction events with Science Olympiad, and we are going to talk engineering just a little bit today. We're going to talk engineering a lot in session 3 and 5. And when they do an engineering project, like for Olympiad, they might do a car, some type of car, whether it's a gravity car or a mousetrap car or a battery powered car or an airplane or a rocket or a Mission Possible. That's my event I run, device. If they build one of those for Olympiad, it's going to have certain specifications for Olympiad. And if they're doing an engineering project and they're going to take that to a fair, they need to be trying to solve a specific problem with theirs. So it's possible that you might use one of the designs for one of the things that you build for Science Olympiad and do actual research with that to try to overcome or solve a certain problem, like maybe what are the best materials for this, or what's going to make the strongest device, or what if you might be doing a bridge or a tower. And we are going to do a tower here in this workshop, and Olympiad does bridges and towers and cantilevers and things like that. So it might be, that you could do an engineering project with one of those. It's very, very possible, but it would have to fit the criteria for the science fair to be entered into the science fair. And of course, when you take it to the Olympiad, you've got specifications you have to meet at the actual Olympiad. I don't see a problem with that. I think there are many ways you can meet the specifications with the Olympiad and still have something that's really a unique design that you try to solve a problem with. So yeah, the answer is a long answer. It is possible, yes.
Okay. All right. So again, I mentioned those rubrics when I was on the Science Buddies webpage in the teacher section, and those are there. They're a nice step for you to be able to get started and trying to answer do the grading for those projects. So let's talk a little bit about how scientific research is actually done. And you start off, first of all, with that topic. And I mentioned that's the hardest part, because students sitting there and go, I can't think of anything. And I sympathize with them. I've been there before too. That's why you're encouraging them to ask them questions like, well, what do you do when you're at home? What are your favorite activities? Do you, whenever you have free time, trying to get them doing something that they would have a natural interest in. Once they do that, then they have to develop a testable question. And when they are developing that testable question, we're gonna do that. That's going to be one of your assignments for next week, is to do a testable question. We're going to go through it. But they have to be able to know what they're going to be doing, what's going to be changed for them to be able to measure it, and then how they're going to know whether or not that's effective. And with that, they have to look at safety issues, and is this doable? Can I get materials around to be able to do a project with this along the way? Or, you know, would I have to have an expert helping me? And those types of things that you start looking at. And as you're developing that, you're going to be doing a literature review to find out, do we already know the answer to this question? Does everybody already know how to do this, or am I wasting my time? All I need to do is you know, look it up on here, and everybody, all the students will definitely go to Google something to see if we already know how to do it. And if it comes up we already know how to do it, then they need to come at it from a different approach. Well, we can do it this way, but maybe that way. But that literature review is very important. Again, you need to know what we know before you can figure out what we don't know to be able to develop a good independent project. Then they have to develop whatever that method's going to be. I usually call it a research plan. And to be able, what materials am I going to need? What processes am I going to use? What steps am I going to take in doing my experiment? What are my safety issues that I need to be addressing? Am I in elementary school and I need to be working with something, you know, I'm a third grader, but I need to work on the stove. So is that an issue? Yes, that's an issue. You have to have someone supervising you along the way. So looking at those safety issues from something as simple as that as to something, you know, are they working with a chemical that's potentially hazardous, and they need to be working in a special environment to be able to do this. So those are the things that need to be addressed, and the bibliography is always included with that research plan, so that when you look it over, you know that the student actually has found out what are these issues that I need to be addressing in that background research or the literature review. Once they have that study design or the research plan, then they finally can start doing the experiment. And once that's been approved, that research plan's been approved. Don't forget that approval process. And it's very important that you read those research plans very carefully, because you don't want the students to do something that could be potentially hazardous or harmful, and no one has addressed that concern. And if the student gets hurt along the way, then it comes back to, well, the teacher said it was fine for me to do that. And this is part of the reason why we really say, if you use those rules that come from ISEF, the International Science and Engineering Fair, that helps you address a lot of those issues. And it takes the heat off of you from having to say, no, you can't do that, because you can say, no, the rules say you cannot do that. And we have to go by the rules. And so you're not the heavy, the rules are the heavy. But then you actually get around to testing and measuring and conducting the experiment that you have done. You collect data along the way. Every step of this is in that journal that you have started at the very beginning, by the way. And each time you do a journal entry, it's dated. You can take photographs and take them into the journal along the way, and write down not only quantitative but qualitative data as they're doing the experiment. They have to be able to analyze the data that they have collected, and this is a great time to get the math people in there to help them. And it shows that math and science are very, very closely related, that we depend upon both of math and science to be able to tell the story and give us the correct interpretation to help us come up with the conclusions that we need to be. And very often, once you finish that one experiment, you have come up with more questions that now are not answered that along the way. That, well, this is what I came up, but if I did it this way, I wonder what would happen instead. So this is why it's a circle. It doesn't just stop at the ending of one thing, but hopefully it will increase a student's excitement and want them to go a little bit further along the way. Engineering process is a little bit.
Let me interrupt you there. When I was young, I used to do oceanographic research. And many times we would have an experiment designed, and we'd be out in the ocean, we'd be collecting data. And we collect the data and do everything that Judy said and get to the end of that cycle. And a lot of times we would create more questions than we answered. and we'd have to design another experiment to go even further and maybe have different variables and whatever. So it was very often that one experiment led to another, led to another. So it is a cycle that you keep going through sometimes. Thanks, Judy.
Okay,
Great.
well,
There's also a
read
good
in the
question.
chat. Is that Teresa?
Oh,
What you,
yeah. Go ahead, Judy. If you saw it, go right ahead.
I saw it. I was checking. So while you were talking, Manley. And this is a great question, and from the liability perspective. And this is why we're going to talk about the forms that they have for the International Science and Engineering Fair. And along the way, the forms are signed by students, the forms are signed by parents, and the forms are signed by you who is overseeing things. And with that, the parent says that they have read that research plan and they know what the student is going to be doing. And they also say that they have looked at the rules. And you sign that you've looked at the rules and regulations too. And by relying on those international science and engineering rules, it really helps you avoid a lot of those potential liability issues. It keeps them from doing some of the activities that even the parents don't think are dangerous. Gosh, one year I had a parent who signed off as the qualified scientist. Okay, it was the parent. Conflict of interest right there. Okay, he's a beekeeper. His daughter was doing a research on the effect of bee stings on different parts of your body. The father, who had signed off as the qualified scientist, was the subject, one subject, okay? The daughter was stinging her father in various parts of his body and measuring the reaction in various parts of his body from the bee sting. Now, I have a very good friend who is a beekeeper and is also a biological researcher, and she went ballistic because she was saying, does he not realize that you can develop an allergy and go into anaphylactic shock at any time, even though you've been stung by bees many times? And so no one read that and thought that that was a problem because the father signed all the papers. And nobody else saw it until it was already done. So if you plan in that timeline and actually go over those research plans and ask for safety issues and look at the rules, then you can get other people's eyes on things. So it's not just you. And then if something does happen and the parents, especially if they're working at home, and the parents have said, oh, sure, that's no problem, they can do that. When you have said, no, that is not approval, then that helps take the liability issue off of you.
Foremost, it protects the student. Want to protect the student. But
right.
Secondary thing is it protects the teacher too.
Yes. But if they abide by the ISAF rules and regulations, they are not going to be running in. They will not be allowed to do a lot of the things that would be potentially harmful because they are pretty strict about it. And if anybody questions you, the International Science and Engineering Fair is the largest student research organization in the world. And the rules and regulations that they have developed are accepted across the world. And we take students to the international competition, and there are about 1,700 students from about 70 different countries that participate, and they all have to enforce these same rules and regulations.
Yeah. And so I think, Judy, we need to move forward, but I did drop the rules into the chat for you. Right. And I wanted to let everybody know that we will actually spend a decent amount of time on safety and things like that in session 4.
I just looked at the time. Thank you.
Yep.
You have to keep track of me. Engineering process, you'd come up with a problem. So it starts off with the ask, where you have to identify what the need is or what the problem is and what your constraints are in being able to solve that problem. And the constraints are really important to be able to work within. Then you have to do the background research, the same as you did in the scientific problem. You have to come up, after doing the background research, you have to imagine different ways to be able to solve the problem. Then once you come up with something that you think is promising as a way of moving forward, you develop a plan, and that would be what we consider that research plan. And when they're doing that background research, they're doing a bibliography at the same time. Now with engineering projects, they build a prototype that they will then test. And that is a kind of a circular process of building a prototype, testing it, seeing how it works, seeing where it needs to be improved, then going back and rebuilding it, and then testing it and improving it until they get to the point that they feel like, okay, this is now what I want to present as my solution. So often students only have time to do that one build and come up with something. But if they have time, then I would encourage them, once they do the testing, to see if they can improve it along the way. So the link that I have down here on the Teach Engineering is a great resource. And I think Teresa's got a few more that she may be able to drop in the chat as well.
Judy, we've got 4 minutes on this session.
Okay, all right. Scientific and engineering practices. So let me see. All right, so yeah, one more slide. We may not be able to get the videos in, but one more slide. The differences are scientific, you're asking questions. Engineering, you're defining a problem. You're developing using models in the engineering practices or the engineering design. And in scientific, you're going to be planning and carrying out an investigation. With the scientific portion, you think you know how it's going to work, and you're trying to prove that that is the way it works. Whereas with the engineering design, you're trying to make a solution to a problem. You're trying to do that need. With both, you'll be analyzing and interpreting data. With both, you're going to be using mathematics and computational thinking. You have to construct the explanations of why something is working that way, why it doesn't work that way for science. In engineering, you're designing solutions. Both, you have to engage in argument from evidence of what you are seeing along the way. And you have to obtain your data, you have to be able to evaluate your data, and you have to be able to communicate that to other people. And the communication portion of it is the part that wraps up the entire project, which makes the student really understand what was going on and where they need to go. So I didn't get my senior link in here, I'm sorry, but I've got 2 minutes, and this is a 2-minute video. Here is an elementary student that came up with a neat project. Let's see if it will play, and I'll have to change that and get my other sharing on.
My name is Abigail, and my project, Sound Advice, was presented
Okay.
in the elementary category.
Oh, it is.
My project was to measure how loud it is in our school cafeteria.
Let me start it back from the beginning.
Yeah, I think you got to turn it up a little too, Judy. Please.
Okay.
My name is Abigail, and my project, Sound Advice, was presented in the elementary category of the science fair. My project was to measure how loud it is in our school cafeteria and see if we could be getting hearing damage from it. I did this because it was getting very loud in our cafeteria, and I wanted to see if it could actually be hurting us. I measured the decibel levels in our school cafeteria and found that we were above the safety limit for how loud a place can be. Students who are in the cafeteria for 30 minutes can be getting hearing damage, and it's even more for staff who are in there for hours a day. I think that there needs to be a solution to this because it can be damaging to our health.
Okay, so let me go in here, stop sharing that. Actually, I'll stop sharing my screen completely. Okay.
Judy, while you're looking, Teresa, do we need to tell everyone, do they need to go click on session 2, or can they just stay on here?
No,
So yeah, I do want to talk to folks about that. Judy, are you all set?
For session 2 or for ending this? Yes.
for ending this. Okay, great. So